Hey there, welcome to another deep dive. Ever wondered how mathematicians make sure your online messages stay safe? Like, how do they keep prying eyes out of your business?
It's really quite amazing when you think about it.
It really is. And today we're going to crack the code of cryptography with a deep dive into the world of primitive polynomials.
Sounds a bit intimidating.
It does sound kind of intimidating, right?
Yeah.
But stick with us. This stuff is way cooler than it sounds.
Oh, it really is. These polynomials are like the secret ingredient behind everything from keeping communication safe and secure to those error-correcting codes that make sure your data doesn't get corrupted.
Exactly. They're like the unsung heroes of the digital age.
Absolutely.
So to guide us through this fascinating world, we're diving into some really cool research by Gerardo Veiga. And let me tell you, one of the first things that caught my eye was the notation.
Oh, yeah.
Have you ever seen a mathematical paper?
Oh, tons.
It's like reading hieroglyphics.
It's like a whole other language, isn't it? It's like deciphering a secret code sometimes.
Right. It's like they're trying to keep their secrets hidden from the uninitiated.
Exactly.
But really, it's all about efficiency, right? Creating a shorthand for these really complex ideas.
Absolutely. Precision and conciseness.
Right. So, for example, you'll see this IFQ, which kind of looks like something straight out of Star Wars, but really it's just short for a finite field. Imagine a set of numbers, but instead of going on forever, they're playing by a unique set of rules. That's your finite field.
Yeah, it's like a little self-contained universe of numbers with its own special laws of arithmetic.
I like that. A self-contained universe of numbers. And here's where it gets really neat. That little q isn't just any random number. It actually represents a prime number, like 2, 3, or 5 raised to a power. And this might seem like a tiny detail, but it hints at some really big mathematical structures we're dealing with.
It's like a little breadcrumb leading you to a deeper understanding.
Exactly. It's like those Easter eggs that programmers hide in code. Now, this paper also throws around terms like order and quasi-order of a polynomial, which,
Yeah, those are good ones.
I know, right? Which might sound a bit like abstract mathematical jargon.
Well, think of it this way. Imagine you're tracking a satellite orbiting the Earth right. The order of its path tells you how many orbits it takes to return to its exact starting point.
Ah, so we're talking about cycles, repetitions, kind of like the rhythm of a song.
Precisely. Now, when we talk about the quasi-order of a polynomial, imagine that same satellite. But this time, its orbit shifts slightly each time it goes around the Earth.
Okay, so it's not a perfect loop anymore.
Exactly. It's like a dance where the steps are similar, but not quite the same each time.
I like that. It's like a cosmic waltz.
Exactly. And the quasi-order helps us understand this slightly less predictable pattern. It's about finding where that pattern begins to echo its earlier path, even if it's not a perfect loop.
Okay, I'm starting to see the elegance in all this. So now that we've got a handle on the lingo, let's jump into Theorem 1.
All right, Theorem 1. This is where things start to get really interesting. It gives us this powerful tool to identify those special polynomials that have what it takes to be primitive. It's like having a metal detector that only beeps when you're standing right over a buried treasure chest.
I love that analogy.
It helps us cut through the noise and focus on the real gems, those primitive polynomials. You know what's really cool about Theorem 1? It paves the way for Veiga to really zoom in on a particular type of polynomial, those of degree 2.
Ah, degree 2. So that's where the highest power of x is 2, right?
You got it.
Like x plus 2x1.
Exactly. That's a perfect example.
Okay, but why are those so special to mathematicians? Why focus on degree 2? What's the big deal?
Well, they're special because they're kind of like the simplest ones that can have this primitive quality we're so interested in.
Okay, so they're like the beginner's guide to understanding these primitive polynomials.
Yeah, you could say that. They're like the Lego bricks of this mathematical world.
Yeah.
Simple on their own, but you can build incredibly complex structures with them.
I love that analogy. Legos, gotta love them. So, with these degree 2 Lego bricks in hand, Veiga throws us proposition 1.
Right.
And listeners, bear with me here because we're going to get a little bit into the weeds here.
And they're about to get real.
It is. It is. Proposition 1, basically it says if a degree 2 polynomial, if it starts with a 1, you know what I mean?
Like a leading coefficient of 1, we call those monic.
Right. Monic, there it is. I knew there was a name for it. So if it's monic and it fits a certain pattern, then all its terms except for the constant at the end, they got to be non-zero.
It's like he's setting the ground rules for these polynomials. Like, hey, if you want to play in the primitive club...
These are the rules.
Exactly. And these rules are important. They help Veiga prove even more complex things about primitive polynomials. And that's where proposition 2 and corollary 1 come in. They're like the next levels in the game.
Okay, I'm following. So what do these next levels tell us? What are we learning here?
So with proposition 2, Vega finds this connection between different polynomials that have the same quasi-order. Remember our satellite analogy?
Yeah, the slightly shifting orbit.
Right. So it's kind of like saying, even though two satellites might have different paths, if their quasi-orders are connected, there's still like a harmony in their movements.
Interesting. So even though they look different, they have this underlying connection, this shared rhythm. That's pretty neat. Okay. And then does corollary 1 just kind of reinforce that idea?
Yeah, corollary 1 takes that connection and strengthens it. It's like saying, hey, we've spotted these two satellites with related quasi-orders, and guess what? That's not just a coincidence. That similarity actually tells us something really important about how they behave over those long stretches of calculations.
Yeah.
And, you know, that whole idea about the echoing patterns of the quasi-order, that's about to get even more important as we head into the heart of Vega's research. Theorem 3.
This is where it gets really juicy. Theorem 3, it's like the magic key or something.
It really is.
To identifying these primitive polynomials, it's like
Yeah.
Vega's giving us this shortcut, this express lane to finding these mathematical treasures.
It's not just about speed, though. It's like, imagine you're trying to find a specific grain of sand on the beach, right? Vega's method is like having this sieve, and it filters out everything except for that one grain you're looking for.
Wow, that's a really cool way to put it. Okay, so Theorem 3 gives us this powerful tool, this sieve. But what I really appreciate is that Vega didn't just like leave us hanging with the theory, you know? He actually walks us through these practical examples.
Oh, absolutely.
Which is so helpful for really wrapping our heads around how this all works in the real world.
He gives you the map, and then he takes you on the treasure hunt.
Exactly. So in example 2, he takes us on this adventure to the world of IF11, which is, it's a finite field with 11 elements, and his goal, to figure out which polynomials in that specific field are the special primitive ones.
It's like a detective story.
It really is. And this is where that whole idea of the quasi-order, those echoing patterns, it becomes crucial.
Right.
Because remember, Theorem 3 had that second condition, the one that involved checking if the quasi-order of the polynomial matched up with what we'd expect for a primitive polynomial.
Right. Had to match up.
Yeah, and that involved some polynomial long division, which, I'll be honest, it seemed a bit intimidating at first.
Yeah, it can look a little scary.
But Vega, he makes it look like a walk in the park.
He's got the magic touch, doesn't he?
He does. Like in example 2, he just breezes through these calculations. And based on the results, like whether or not all those terms are non-zero, he can immediately tell you, primitive or not, this is the polynomial you're looking for.
It's like he has this intuition, this sixth sense for spotting those primitive polynomials.
It really is remarkable. And then in example 3, he takes us even deeper into this mathematical jungle, venturing into IF8, which is a finite field built on top of IF2.
This is where you see how versatile Vega's method is. It's not just a one-trick pony, you know. It can be applied to all sorts of different situations, different finite fields, and still reveal these hidden structures.
Exactly. It's like a Swiss Army knife of mathematical tools. And with just a few, elegant calculations, boom, Vega pinpoints those primitive polynomials in IF8.
Elegance. That's the beauty of math, isn't it?
It really is. It's not about brute force. It's about finding that elegant solution. So to wrap things up, we've explored this new, super efficient way to identify these super important primitive polynomials, all thanks to Gerardo Vega and his awesome research. But this is so much more than just some abstract mathematical puzzle, right?
Oh, absolutely. This stuff is the backbone of modern technology.
It really is. I mean, these polynomials, they're working behind the scenes to keep your online shopping safe.
Secure communication, data storage.
It's incredible.
They're everywhere.
They really are. They're everywhere. So next time you're streaming a movie or sending a text message, take a moment to appreciate the power of these hidden mathematical heroes.
Ah, the silent guardians of the digital age.
I like that. The silent guardians. Well, this has been a fascinating deep dive, and I hope you've enjoyed exploring with us. Until next time. Welcome to another deep dive. Today, we're going to be looking at this research paper,
Right.
and it's called, get this, a characterization and an explicit description of all primitive polynomials of degree 2 over finite fields.
Okay.
It's a mouthful, I know,
Yeah.
but trust me, this stuff is way more interesting than it sounds.
Absolutely.
And you might even be surprised to learn that it actually has a lot to do with the tech that we use every single day.
It really does. It's one of those areas where the math can seem kind of abstract,
Right.
but it has a huge impact on how we live our digital lives.
Yeah, It really makes you think, like, how do computers handle these crazy large numbers and still, keep everything secure?
It's a really interesting challenge, especially as we keep pushing the limits of what computers can do.
Exactly. And that's where these things called finite fields and these primitive polynomials come into play.
Right.
So imagine like a clock face, right? It only goes up to 12 and then it loops back to 1.
Okay.
A finite field, it's kind of like that. It's this closed loop of numbers, but with its own, special set of rules.
Yeah. It's a really clever way to represent those big numbers, but in a way that we can actually manage and work with. And the amazing part is that they underpin a lot of really important technology, like cryptography, which is how we keep things secure online.
Right.
And even error-correcting codes, which make sure that, when you download a file, it's not corrupted.
So it's like the finite fields are the playing field, right?
Okay, yeah.
But then we need players.
Yes.
And those are our primitive polynomials.
Exactly. Those are the tools that help us unlock the potential that's in these finite fields.
Okay, so in this deep dive, we're going to really try to unpack how this paper gives us a new way of looking at these primitive polynomials.
Yes.
And how we can identify them, and ultimately how this all leads to more efficient and secure systems.
It's really about, I think, making things more streamlined than some of the previous work in this area.
Okay.
It helps us really pinpoint these mathematical objects and understand them better.
Right. So they start off by talking about these things called cyclotomic classes.
Right.
And I know that sounds a little intimidating, but
It's a mouthful.
Yeah, but imagine like a city map.
Okay.
Right? And all the different neighborhoods, each one has its own like vibe, its own thing going on.
Right.
Cyclotomic classes are kind of like these neighborhoods within the finite field.
Yeah.
And knowing where a polynomial sort of lives in these neighborhoods actually tells us a lot about it.
It helps us classify things.
Oh,
We can figure out very quickly if a polynomial is going to be a primitive one or not, just based on its characteristics.
Oh, so it's like we don't have to go knocking on every single door. We can kind of narrow it down by neighborhood.
Exactly. We can be much more efficient with our search.
I like it. So that's where this theorem 3 comes in.
Yeah.
They call it like a litmus test.
Yeah, it's a really good way to think about it.
So it's like a set of conditions. If a polynomial meets these conditions,
Yes.
boom, it's primitive.
Exactly. It gives us a very clear way to identify them.
Okay, so we have our checklist.
And then they have this other thing, condition B, I think they call it.
Right, condition B. And this one involves something called polynomial division.
Polynomial division.
I know it sounds a little technical.
Yeah.
But bear with me.
So polynomial division, condition B, what's that all about?
Well, it's kind of like a filter, you see.
Yeah.
It helps us separate the primitive polynomials from all the rest.
Okay, so it's like a sieve.
Yeah, exactly. It only lets the special ones through, And the way it does that is by looking at the order of a polynomial.
Order. Okay, now we're getting into some new territory here. What is that?
So basically, every polynomial in a finite field, it goes on a little journey when you keep multiplying it by itself.
Okay.
It cycles through different values, and eventually it loops back to the start.
Oh, interesting. And the order of that polynomial, that's just how many multiplications it takes to get back to where it started.
Okay, so it's like the length of the polynomial's journey around the finite field.
Exactly. A perfect way to put it. And condition B, it essentially checks if the polynomial's journey is the longest possible journey it could take within that field.
So it's looking for the polynomials with the most winding, scenic routes, I guess you could say.
Precisely. And if it finds one,
yeah,
that's a good indication that you've got yourself a primitive polynomial.
Okay, that makes sense. So we've got these cyclotomic classes, these neighborhoods.
Right.
And then we've got condition B, our trusty sieve.
Yeah. It's all coming together.
It's all about finding those special polynomials. But this is just for, finding them one by one, right?
Well, that's where things get really interesting. You see, so far, we've been talking about identifying individual primitive polynomials.
Right.
But theorem 4 in this paper, it takes things to a whole new level. It's like it gives us this really elegant way to list out all the primitive polynomials of degree 2.
Well, wait, hold on.
Yeah.
So instead of finding them one by one, this theorem gives us a whole list.
A complete list.
Wow. That's incredible.
It's a game changer, especially when you're dealing with these larger, more complex finite fields. It's like having a blueprint.
So it's like instead of searching for a needle in a haystack, we have the whole haystack.
Exactly.
All the needles are neatly labeled and ready to go. But how do they even begin to do that?
Well, They introduce this really neat idea, this subset called, they call it I delta.
Okay.
And it acts as a filter. It sifts through all the possible polynomials and narrows it down to just the ones that have the potential to be primitive.
Ah, that's clever. So it shrinks the haystack down to a more manageable size.
Exactly. And once you've got that filtered set of possibilities, Theorem 4 swoops in.
Okay.
And it gives you these rules, a set of instructions for how to combine those elements to create all the primitive polynomials of degree 2 in that finite field.
Wow. So it's like having the ingredients and the perfect recipe, and you know it's going to turn out right every time.
Exactly. And the paper, to their credit, they actually walk through a few examples.
Oh, good. I always like to see things in action.
Yeah, they go back to those finite fields with 8, 9, and 11 elements, and they show how Theorem 4 can generate that complete list of primitive polynomials.
So they're like, look, we're not messing around. This actually works.
Exactly. It's really quite elegant and quite powerful. And to top it all off, the way they do it, it connects back to this really fundamental idea in mathematics, Euler's totient function.
Euler's totient function. Okay.
Yeah, it's ringing a bell.
It rings a bell, but you might have to refresh my memory a little.
So it's often represented by this symbol, phi n. And essentially what it does is it tells you how many positive integers there are that are less than or equal to n, but that are also relatively prime to n.
Right, right. Now it's coming back to me.
Yeah, and in the context of finite fields, it's directly related to how many primitive polynomials you can actually find.
So they've shown that their method for listing these polynomials lines up perfectly with what Euler's totient function would predict.
Exactly. It's like this really beautiful harmony between this new discovery and this established mathematical principle.
It's like finding this hidden connection between two seemingly different parts of math.
Exactly. And it just highlights the elegance and interconnectedness of these concepts.
It's really quite amazing when you think about it, how all these pieces fit together so perfectly.
It really is. And it makes you wonder, what other hidden connections are out there just waiting to be discovered.
It really makes you realize how much goes on behind the scenes of the tech we use every day, huh?
It really does. And it just goes to show you, the power of abstract math.
Right.
And how even though most people might not be thinking about primitive polynomials in their everyday life,
right,
the work that's being done here, it really has the potential to change things, to make things faster, more secure.
Absolutely. Like having a better understanding of these primitive polynomials could lead to like faster downloads.
Exactly.
More secure online transactions.
Exactly. More efficient systems all around.
Yeah.
And it all comes from these fundamental ideas.
It's amazing. Okay, so as we wrap up this deep dive,
Sure.
What would you say are the biggest takeaways from this paper?
Well, for me, it's the elegance of this new approach. This new way of characterizing primitive polynomials.
Yeah.
It's like they found a more intuitive way to look at these really complex mathematical objects.
They've given us a new set of tools to explore finite fields.
Exactly. A new map, a new compass, And the fact that it all ties back to something as fundamental as Euler's totient function, it just makes it all the more beautiful,
It's like they've revealed this hidden structure, this underlying order that connects all these different ideas.
Precisely. And it really makes you wonder what other connections are out there.
Right. What other mysteries are waiting to be unraveled?
Exactly.
Well, that seems like the perfect note to end on. If you've enjoyed this deep dive into the world of primitive polynomials.
And Euler's totient function. Don't forget that.
And Euler's totient function. Yes, of course. We encourage you to keep exploring. We'll have a link to the research paper and some other resources on the episode page if you'd like to delve a little deeper on your own.
Yeah. And if you have any aha moments, any questions that come up as you're reading, please leave us a comment.
Absolutely. We love hearing from you. And until next time, keep those minds curious. All right, so get ready, because today we're diving into a fascinating realm of math. We're talking about primitive polynomials.
Oh, yeah.
But don't worry.
It sounds pretty complex.
You don't need like a math PhD to follow along. We're looking at a new research paper, and it was actually just submitted today. So we're going to break it down and extract the juicy insights.
Fresh off the press.
Exactly. It's like getting a sneak peek at the cutting edge of mathematics.
And a sneak peek with some exciting implications, I think.
Yeah.
especially in cryptography and computer science. These are really important concepts.
Okay, so let's unpack this a little bit. The paper is titled A Characterization and an Explicit Description of All Primitive Polynomials of Degree 2 over Finite Fields.
Catchy.
Right. Before your eyes glaze over, let's simplify things. Imagine a clock, like a standard 12-hour clock. If you add 5 hours to 8, what do you get?
You get 1.
You get 1, not 13.
Right, exactly.
And that's the fundamental concept of a finite field.
Yeah, you're working with a limited set of numbers, just like on that clock face.
So there are prime numbers and numbers that are like powers of primes, and these are the building blocks of these fields.
Yeah, the number of elements in a finite field is always a prime number raised to some power. And it's really crucial, this power of primes concept, in areas like cryptography. Like every time you send a secure message online, you can thank finite fields. They're the workhorses behind a lot of encryption algorithms.
So we've got these finite fields, but then within those fields, we have primitive polynomials. What makes them so special?
Think of them like the superstars of finite fields. They have these unique properties that make them so useful for generating sequences of numbers. Imagine you have a deck of cards. A primitive polynomial is like a specific shuffling technique that makes sure you go through every single card in the deck, but in a very predictable way.
And in encryption, that predictable shuffling is key, right?
Yeah, you got it. The more robust and unpredictable that shuffling is, the harder it is to crack the code.
So how do we find them? These special polynomials, I mean, that's where this paper comes in, right?
Yeah, finding these perfect shuffling techniques isn't easy.
Right.
And this paper offers a new way to identify these elusive primitive polynomials, specifically those of degree 2.
Degree 2.
Yeah, it's like the fundamental building block in this world.
So degree 2 just means we're dealing with polynomials where the highest power of the variable is 2. So like x squared plus something x plus something.
Exactly. You got it.
Okay. Now, this paper is focusing on a new method for characterizing and finding these polynomials. And they're saying it's more like elegant and efficient than previous techniques.
And they walk us through their process with examples, almost like they're taking us by the hand and saying, look how simple and elegant this can be.
Okay, well, let's get into those examples. Seeing is believing, right?
Absolutely. Let's start with example 1. They use a finite field with 13 elements, where 6 is what we call a primitive element, kind of like our starting point for generating other elements.
Okay, I'm with you so far. So they use this example to illustrate how their method works.
Exactly. They take 2 polynomials, and they show us how to determine whether or not they're primitive using their new method.
And this new way of identifying primitive polynomials, it's based on what?
It all boils down to this clever use of what mathematicians call the quasi-order of a polynomial and some specific properties of finite fields.
Quasi-order. Sounds intimidating.
It's not as scary as it sounds. Think of it like a way to measure how quickly a polynomial helps us cycle through all the elements in our finite field.
Okay, so quasi-order is like a measure of efficiency.
Yeah.
How quickly we're shuffling those cards.
Right.
I like it.
Yeah.
But how does this play out in practice? Let's jump to example 2.
Okay, so in example 2, they've switched gears a little bit. We're using a finite field with 11 elements now. And they really get into the nuts and bolts of their new method here, using a bit more kind of like, hardcore math to illustrate the process. But
yeah, because like equations aren't exactly everyone's cup of tea.
exactly. And the beauty is you don't have to be a math whiz to really grasp this core idea.
Right.
They introduce this concept of dividing one polynomial by another and looking at what's left over the remainder.
Okay, so like long division.
Yeah, like we learned back in like grade school, but with polynomials.
Oh gosh, I vaguely remember long division.
Yeah.
And they use this to determine if a polynomial is primitive.
Exactly. Based on what that remainder looks like, they can
Right.
tell if the polynomial has that unique primitive property.
Interesting. Okay, so it's like we're looking for clues within the division itself. Can you give me a concrete example? What's going on in example 3?
Okay, so in example 3, we're working with a finite field with 8 elements. It might seem a bit abstract,
Right.
but they analyze 4 different polynomials, showing how this remainder method reveals which ones are primitive.
Okay.
It's like they're handing us a magnifying glass to spot these special polynomials.
So we're using polynomial division as like a tool to unlock these secrets.
Yes.
They're not just saying it works, they're really showing us how they get there.
And the exciting part is this method isn't just elegant, it's more efficient than previous techniques.
So we're moving faster.
Yeah.
But like, why should we care about finding these primitive polynomials so efficiently?
Okay, so imagine a world where we can develop even faster, more secure encryption algorithms
Right.
for our online communication. We could design more efficient error-correcting codes,
Okay.
unlock new possibilities in areas like computer science and engineering. That's the potential impact of this.
So faster identification, tangible advancements.
Exactly.
It's like they found a shortcut,
Yeah.
a more efficient route to innovate.
Exactly. And they don't stop at characterizing these polynomials. They actually go a step further and provide a way to explicitly describe all primitive polynomials of degree 2 for a given finite field.
So not only can we find them faster, we can systematically list them out.
It's a remarkable achievement.
What's the secret sauce? How are they generating these polynomials?
Okay, so it all revolves around two special sets. They're called B and J.
B and J.
Right. And remember how we talked about the coefficients of a polynomial? Those numbers that sit next to the variables?
Like the x squared plus something, x plus something?
Exactly. So set B is essentially the set of all possible candidates for the coefficient of that x term.
So B is like the pool of numbers we can choose from.
Precisely.
Okay.
Now, set J is a bit more intricate, but it's all about making sure that the constant term in our polynomial, the number that doesn't have an x attached to it, has specific properties that guarantee primitiveness.
So J is like the quality control,
Yes.
making sure the constant term is doing its job.
Exactly. The recipe involves combining elements from these sets in a specific way.
Okay.
And voila, you've got yourself a primitive polynomial.
They crack the code. But does this recipe work for any finite field? Or are there limitations?
Well, that's the exciting part. They've demonstrated its effectiveness for different finite fields.
Okay.
For instance, in example 4, they use their recipe to generate all 18 primitive polynomials of degree 2 for a finite field with 8 elements.
18, that's a lot of polynomials, and they walk us through how to find each one.
They do. And it highlights the power of their method because it's not just about finding a few, it's about having this systematic, efficient way to generate them all. Imagine, like a chef who can not only bake a delicious cake, but also give you the recipe so you can recreate it flawlessly every time.
That's a great analogy.
Right.
So it's the what and the how when it comes to these polynomials.
It really is. It's the elegance and efficiency of their approach that has me excited.
And it's not just about like quantity, right? It's not about having a ton of polynomials. It's about being able to generate them efficiently.
Yeah, exactly.
Without like brute forcing your way through.
You hit the nail on the head. This research gives us a streamlined process,
Right?
like a more direct path to finding those mathematical needles in a haystack.
Okay, I'm convinced. This recipe is a game changer.
It is.
But what about other finite fields? We talked about examples with 8 elements, 11 elements. Does it hold up? What happens in examples 5 and 6?
Well, in examples 5 and 6, they put their recipe to the test.
Okay.
With different finite fields, one with 9 elements, another with 11. And guess what?
It works flawlessly.
Exactly. They successfully generate all the primitive polynomials of degree 2 for those fields as well.
So it's like a universal key,
Yeah, it's really quite remarkable.
unlocking all these doors. So we've gone from understanding what finite fields are to seeing how these special polynomials operate within them. And now we've got this powerful recipe to find them. It's like we've scaled a mathematical mountain
It's quite a journey.
and we found the treasure chest at the top.
And the view from up here is pretty incredible.
So as we're admiring this view,
Yeah.
tell us, what does this all mean? Why should we, like the non-mathematicians, be
Well-
excited about this? Paint us a picture of the future.
Imagine a world with even faster, more secure online communication, where data transmission is nearly flawless, where complex computations in areas like computer science and engineering become significantly more efficient.
Wow.
That's the potential.
All thanks to polynomials. It's amazing how something so, I don't know, like seemingly abstract can have such a tangible impact.
Absolutely. It speaks to the interconnectedness of it all, right?
Yeah.
And, the paper focused on degree 2 polynomials, but it really opens up these exciting avenues for further exploration.
So like a stepping stone to even more complex polynomials. What lies beyond degree 2?
Precisely. Imagine if we could apply these techniques to higher degree polynomials, unlock even more intricate mathematical secrets.
It's like they've illuminated a path
They really have.
into uncharted territory.
Yeah.
And on that note of uncharted territory, I think we've reached the end of our deep dive. From the intricacies of finite fields to the power of primitive polynomials, we've explored this hidden world.
This hidden world
Mathematical
beauty. It is beautiful.
and its potential to really shape the future.
Absolutely. Until next time.
All right, dive buddies, get your metaphorical scuba gear ready because today we're plunging headfirst into the deep end of finite fields and something called primitive polynomials.
Yeah.
We'll be using Gerardo Vega's recent research as our guide.
And a fascinating guide it is. Imagine trying to find a specific grain of sand on a beach.
Oh, wow.
That's what identifying these special polynomials used to be like. But Vega's work is changing the game.
Okay, I'm intrigued, but before we get lost in a sea of numbers, can you give me the quick rundown? What makes Vega's approach so groundbreaking?
He's found an elegant way to link these primitive elements. Think of them as the VIPs of a finite field with a special type of polynomial, specifically those of degree 2. It's a connection that simplifies the identification process significantly.
So it's like he found a shortcut through a mathematical jungle. And why are these degree 2 polynomials so important?
Think of it like this. They're simpler to work with, especially in applications where computing power is limited. It's like using a smaller, more agile tool without sacrificing effectiveness.
Makes sense. But I have to admit, the concept of a finite field still feels a bit abstract to me.
Well, imagine a clock face where you only have 12 numbers.
Okay, yeah.
Once you hit 12, you circle back to 1. Finite fields are similar, but instead of hours, they have a set number of elements determined by, interestingly enough, prime numbers.
So instead of a number line that stretches out forever, it's more like a mathematical dance floor with specific boundaries.
Precisely. And within this dance floor, the primitive polynomials are the ones leading the most intricate and fascinating routines. They have this unique ability to generate all the other elements within that specific field through a series of operations.
Okay, that's pretty cool. They're like the choreographers of the finite field, making sure every number knows its steps. But how does this translate into something like, say, online security?
Let's say you're sending your credit card information online. These primitive polynomials underpin the encryption algorithms that scramble your data, making it virtually impossible for anyone but the intended recipient to decipher.
So they're like the guardians of our digital secrets.
Exactly. They ensure secure communication in a world that increasingly relies on it. And what's remarkable about Vega's work is that he focuses on these degree 2 polynomials, which are particularly useful for devices with limited processing power, like smartphones.
So even though the math is complex, he's finding ways to make it work efficiently in our everyday lives. That's fascinating. But how does he actually simplify this process of identifying these powerful polynomials? I took a peek at the paper and it's still pretty dense.
You're right, it's not exactly light reading. But what Vega does is break down this complex problem into manageable cases, almost like creating a roadmap.
Uh-huh.
He looks at the characteristics of a finite field, and for certain cases provides a clear set of rules to determine if a polynomial is primitive. It's incredibly efficient.
So instead of wandering aimlessly in a maze of numbers, he's provided a map and a compass. That does sound helpful.
Exactly. And for those more complex cases where a straightforward set of rules isn't possible, he introduces a new method, a more efficient technique, that uses what he calls a Boolean function, a concept we'll unpack in more detail later.
Okay, color me intrigued. Now, I noticed the paper also mentions something called cyclotomic classes. How do those fit into this mathematical puzzle?
Remember our finite field dance floor analogy? Imagine dividing that dance floor into sections.
Okay.
These sections are like cyclotomic classes, and they play a crucial role in organizing and understanding the relationships between the elements in a finite field.
So it's all about understanding not just the individual dancers, but also how they interact and move together as a group.
Precisely. And Vega uses these cyclotomic classes to refine the process of identifying those all-important primitive polynomials. He's even developed a way to determine a polynomial's order, which tells us how many times you need to apply a specific operation to an element within a cyclotomic class before it cycles back to its starting point.
It's like figuring out the steps of a complex mathematical dance, right? So is a higher order better for something like encryption? Does it make the code harder to crack?
You're on the right track. A higher order can indeed make encryption stronger, but it's not quite as simple as just picking the highest number. Think of it like the order of a polynomial is like the number of steps in a dance routine before you land back in your starting position. A longer, more intricate routine, one with a higher order, is generally harder to predict and replicate.
So a more complex dance equals a more secure code. That makes sense. But Vega's work goes beyond just understanding these orders, right? He actually provides concrete tools to identify these crucial polynomials.
Absolutely. He focuses on a specific type of polynomial known as an irreducible polynomial. These are like the prime numbers within a finite field, the building blocks that can't be factored any further. Specifically, he dives deep into degree 2 irreducible polynomials and their fascinating connection to those all-important primitive polynomials.
So he's zeroing in on a specific type of building block that's particularly valuable for constructing these secure codes.
Precisely. And what makes his research so compelling is that he doesn't just stop at the theory. He shows us how to actually find and characterize these special polynomials using the unique properties of finite fields. For instance, remember those primitive elements we talked about earlier?
The VIPs of the finite field, how could I forget?
Right. Well, Vega demonstrates that by carefully selecting specific primitive elements and understanding their order, we can efficiently pinpoint those hidden primitive polynomials. He introduces this ingenious tool, a Boolean function, that acts like a filter, separating the primitive polynomials from all the others.
Okay, so it's like having a metal detector on a beach, but instead of beeping for buried treasure, it beeps for these special polynomials.
That's a great analogy. And the beauty of it is that Vega provides clear, step-by-step examples to illustrate his methods. He walks us through specific finite fields, showing us exactly how to apply these techniques.
That's what I like to hear, concrete examples, because honestly, whenever we talk about advanced mathematical concepts like this, I always wonder about the real-world applications. So besides keeping my online shopping habits safe, what else can we do with these powerful polynomials that Vega's helping us uncover?
Well, remember how we talked about error correction codes ensuring reliable data transmission? Turns out they rely on the same principles we've been discussing. Think about streaming a movie. Those crystal clear images you see are partly thanks to these codes, working tirelessly behind the scenes to correct any errors that might occur during transmission.
Wow. So from secure online transactions to flawless video calls, these little mathematical objects are the unsung heroes of our digital lives.
Precisely. And what's remarkable is that Vega's work isn't just about understanding these mathematical objects. It's about finding more efficient ways to utilize them. His research has the potential to lead to even faster and more secure encryption algorithms, more reliable communication systems. The possibilities are vast.
It's like he's given us a treasure map, and we're just beginning to explore all the incredible riches it holds. Now, you mentioned earlier that Vega uses specific examples to illustrate his methods. I'm itching to see these techniques in action. Could we walk through one of those examples?
Absolutely. Let's dive into one of the examples Vega uses in his paper. He starts with a finite field that has only 8 elements. It's like a miniature mathematical universe, perfect for illustrating his techniques. He then shows us how to represent the elements of this field using powers of a specific primitive element.
Okay, so it's like that primitive element is the VIP of this miniature mathematical society, and its powers dictate everything else.
Exactly. And Vega systematically walks us through how to figure out which of the polynomials in this field fit the criteria for being primitive, using his streamlined approach and that Boolean function filter we discussed earlier.
So it's like following a recipe step by step to uncover these hidden mathematical gems.
You got it. And to demonstrate the versatility of his methods, Vega doesn't stop there. He tackles a slightly larger field, this time with 9 elements, and shows that even when things get a bit more complex, his techniques remain robust and effective.
That's reassuring to know that these tools can handle the heat. But I imagine there are limits, right? What happens when we start dealing with significantly larger finite fields? Does it become exponentially more difficult to identify those primitive polynomials? That's the million-dollar question, isn't it? What happens when we scale up?
Yeah, Vega acknowledges that while his methods offer a significant leap forward, larger finite fields present a computational challenge. Imagine searching for a needle in a haystack, but the haystack keeps growing exponentially. That's the kind of challenge we're talking about.
So it's like a never-ending game of mathematical hide-and-seek.
In a way, yes. But the beauty of Vega's work is that it doesn't just solve a problem. It opens up new avenues for exploration. His research lays the groundwork for developing even more sophisticated techniques to tackle those larger, more complex finite fields.
So it's like he's shining a light on a path that leads to even greater mathematical discoveries.
Precisely. And the implications of these future discoveries are immense. Imagine developing even faster and more secure encryption algorithms, all thanks to a deeper understanding of primitive polynomials in these vast finite fields.
It's mind-boggling to think that something as seemingly abstract as this could have such a profound impact on our digital world.
And that's the allure of mathematics. It often operates behind the scenes, shaping the technologies we use every day, without us even realizing it. With Vega's work, we're not just unearthing these hidden mathematical gems, but also illuminating the path towards even more groundbreaking technological advancements.
Well, this deep dive has certainly opened my eyes to a whole new realm of mathematics. It's amazing how a single research paper can spark such a cascade of insights and possibilities.
It underscores the fact that there's always more to learn, more to explore, more to discover, no matter how deep you dive.
Absolutely. And on that note, we'll leave you with this thought-provoking question. If these intricate mathematical concepts hidden within the depths of finite fields hold the key to our increasingly complex digital world, what other mathematical secrets are waiting to be unlocked? And how might they shape the future of technology? Until next time, keep exploring, keep questioning, and keep diving deep.
Hey everyone, welcome back to the show. You know how much we love a good deep dive, and today we're taking on a topic you guys have been requesting, primitive polynomials.
It's a fascinating area of mathematics, and we're excited to break it down for you.
Now, I have to admit, when I first saw this paper, primitive polynomials, I thought, oh, this is going to be a tough one. But let me tell you, once I dug in, I realized it's actually pretty cool, like finding a secret passage in a giant library.
It's all about unlocking a deeper understanding of how numbers interact and form patterns, especially in those specialized systems called finite fields.
Finite fields, right. Okay, so for our listeners who might not be familiar with those, could you give us a quick explanation? It's not every day we talk about finite fields.
Absolutely. Imagine a universe where numbers behave a bit differently, like a clock, for instance. Instead of having an infinite number of hours, it cycles back around after 12.
So instead of a number line that stretches out forever, we're working within a smaller, closed loop of numbers.
You got it. And these finite fields, they're not just mathematical curiosities, they're actually the backbone of a lot of modern technology, especially cryptography.
Okay, so finite fields, secret codes, I'm starting to see the connection. But where do these primitive polynomials fit into all of this? What makes them so special?
Well, within these finite fields, you have these things called polynomials, right? And a polynomial, it's basically an expression with variables and coefficients, kind of like a mathematical sentence.
Okay, so like x2, x1, that kind of thing. We've all seen those in algebra class.
Exactly. Now, what makes certain polynomials primitive is their ability to generate all the other non-zero elements within that finite field. It's like they hold a special key that unlocks all the possibilities within that numerical universe.
So it's like having a master key that can open any door in a building.
That's a great analogy, and that's why they're so valuable, particularly in cryptography. This paper, by the way, was just published on September 27th, 2024, and it dives into a really neat way of finding these primitive polynomials.
Hot off the press. Now, the paper focuses specifically on primitive polynomials of degree 2. Do you remind us what degree 2 means again?
Sure. The degree of a polynomial simply refers to the highest power of the variable in the expression. So in our earlier example, x2, x2, x1, that xorius means it's a polynomial of degree 2.
Okay, so it's all about that highest exponent. Makes sense. Now, I'm guessing finding these primitive polynomials isn't exactly a walk in the park, right?
You're right, it can be quite a challenge. Imagine searching for a very specific grain of sand on a beach.
That's a lot of sand. So this paper is offering a more efficient way to sift through all those possibilities.
Exactly. They've developed a method that's especially good at finding these needles in the haystack, these primitive polynomials, particularly those of degree 2, and it's surprisingly elegant.
So it's like trying to find a specific grain of sand on a beach. How in the world do they make that easier? Did they invent some kind of mathematical metal detector?
You could say that. They use this really clever concept called cyclotomic classes. Imagine you're sorting those grains of sand, but instead of just looking at each one individually, you have a way to group them based on certain properties.
Okay, so instead of just having a giant pile of sand, we're dividing it into smaller, more manageable groups based on some shared characteristics.
Exactly. And the way they define these cyclotomic classes is based on some really elegant mathematical principles. It's like having a secret code for figuring out which numbers belong together.
I'm intrigued by this secret code. So once they have their sand neatly sorted into these cyclotomic classes, how do they actually pick out the primitive polynomials?
Well, here's where it gets even cooler. The researchers identified 3 specific conditions that a degree 2 polynomial must meet to be considered primitive.
3 conditions. So it's like a checklist they can use to quickly rule out any polynomials that don't fit the bill.
Precisely. And these aren't just random conditions either. They're derived from some pretty deep mathematical principles. It's like they've cracked the code for identifying these special polynomials.
Cracking the code, I like it.
Yeah.
This is starting to feel like a detective story. Does the paper give us any specific examples of how this works in practice?
They do. They use a finite field with 13 elements as an example and show step by step how they apply their method to pinpoint the primitive polynomials within that field.
So we're not just talking theory here.
Yeah.
They're showing us how this works in action. That's really helpful. We've got our cyclotomic classes, our three-point checklist, and a clear example of how it all comes together. But remember how we talked about those finite fields being like a language that computers use?
Right, the foundation of modern cryptography and all that.
Exactly. So how do we actually bridge the gap between these abstract mathematical concepts and the practical world of computer science?
That's where something called a Boolean function comes in.
Okay, time for a quick tech talk. What exactly is a Boolean function and why is it relevant here?
At its heart, a Boolean function is all about making yes or no decisions. It takes an input, which could be true or false, and spits out an output that's also either true or false.
So it's like a light switch. It can be either on or off.
Exactly. And as simple as that sounds, Boolean functions are incredibly powerful. They're the building blocks of digital circuits and the foundation of how computers think.
So by connecting these primitive polynomials to Boolean functions, they've found a way to translate these mathematical discoveries into a language that computers can understand.
You got it. And that's exactly what the researchers did in this paper. They developed a specific Boolean function that they used to efficiently test whether or not a polynomial fits the criteria for being primitive.
That's incredible. It's like they've created a translator, allowing us to apply these mathematical insights to solve real-world problems. It's like they've given us this incredible tool, this Boolean function, to unlock the secrets of these primitive polynomials. And speaking of unlocking secrets, this paper lays out a sort of master key in the form of Theorem 4, because I got that right?
You've got it. Theorem 4 is where it all comes together. It's like the aha moment, where they reveal the exact formula for identifying primitive polynomials of degree 2.
Okay, so no more searching for a needle in a haystack. They're giving us the exact coordinates. But does it work in practice?
That's the beauty of it. It does. And they don't just tell you, they show you. The paper walks through several examples using finite fields of different sizes just to prove how versatile this theorem is.
So they're saying, look, no matter what finite field you're working with, this theorem has got you covered. That's pretty cool. And they even highlight how to do all of this with as little calculation as possible, right? It's all about efficiency.
Exactly. They've found the most elegant and streamlined approach, which is always the goal in mathematics. But I know what you're thinking. This is all very impressive. But why should someone who isn't a mathematician care about these primitive polynomials?
It's a valid question. We've been deep in the math weeds. But how does this impact the real world?
Well, remember how we talked about finite fields being like the language of computers, especially in cryptography?
Right, the whole secure communication thing.
Exactly. Primitive polynomials are essential for creating the secure codes that protect our online transactions and ensure that our data stays safe.
So it's not just theoretical, it's got real-world implications.
Absolutely. And not just in cryptography. They're also used in things like error correction codes, which make sure that the data we transmit and store doesn't get corrupted.
Wow, so primitive polynomials are like the unsung heroes of the digital age. Who knew?
They're working behind the scenes, keeping our digital lives running smoothly. And the best part is, this research opens up a whole new avenue for exploring even more applications in the future.
That's what makes this deep dive so exciting. We've gone from the basics of polynomials to cutting-edge research that has the potential to shape the future of technology. And that's it for our deep dive today. Thanks for joining us on this mathematical adventure. Until next time, keep exploring the fascinating world of numbers.